Hello, my name is Kamil Czerski, and in deep sense, I'm a lead senior machine learning engineer. And today I would like to show you attention mechanism implemented for graphs and its variants. We will start from something very simple. I would show you baseline attention mechanism. Hopefully, I will be able to explain it well enough so everyone can understand. Then we will go through implementation in graphs of this attention mechanism, what is lacking in attention mechanism that we have to modify to be able to support graphs. And then we would go into a bit more interesting and advanced topic, a RoPE and its application for also for attention in graphs. So our motivation is the need of our client. The client is healthcare pharma, and he's processing a lot of molecular data. These molecular structures are coded, the nodes are coded into features, and we need to support distances somehow. As we will later see, the baseline attention does not support distances. So we need to, on an idea level, propose and implement something. But also the main goal of this project is to speed things up, to deliver very fast implementation. And this would be outside of today's presentation, but I just wanted to mention that it's not that we only implement it in PyTorch, we also have to speed it up. Attention mechanism is actually very simple. You can imagine it's similar to a databases where we have queries that is our questions. We ask the database, we have keys which are in database, and if query matches the key, then we retrieve values. It's only naive comparison, but it works in practice to get intuition that way. First, I wrote down here it in matrix multiplication form, but I would try to go a little. In this matrix multiplication, we start from multiplication of keys and multiplication of queries and transport keys. Then we calculate softmax row-wise for each query, and at the end we multiply probability distribution, which is output from softmax with and the values. So first of all, how we get these queries values. Usually they are like retrieved from some previous layer, which is often also an attention layer. And with just fully connected layers, we mix the features separately for keys, queries, values, and we receive these tensors, these vectors. And then I would like to show you like a visualization of this attention mechanism. So let's look at the K. So we have from 0, 1 to nk, it's our keys. We have Q, it's our queries from 0, 1 to m. And each of a key and query is a vector of features of the same length. They all have same length of number of features. And here I represented them by the fruits. So each query is some fruit, each key is some fruit, and if fruits are similar, we expect to the score, the dot product between them to be higher. So yeah, what is dot product? Of course, everyone knows, but let's see into details in machine learning how it really works. So let's imagine that we have a query, which is a red apple, and we have a lot of keys, but one of these keys is also apple, but it's a yellow. So we see that first feature on the blue rectangle maybe is a color. So for this red apple, for the query is a red information. For the second apple, it's a yellow. And they are like not super similar. So this multiplication will not be a huge number. Maybe this is like 0.5 and this is 0.1. And the second one is how sour it is. So they both are really sour. These features match very well. So multiplication here returns a quite large number. And maybe they are both negative values. So, but 2 minuses give us plus. So still it's a big value, very similar features. And the last feature is how good is for digestion. and this is a bit better, quite matching features. And also, so we multiply it and add together separately. Each feature is element-wise multiplication with feature from the other set. And we have one attention score when we multiply these two vectors. And of course, each query is multiplied with each possible key, and it creates a row in this score matrix. And then, like, we have unstructured numbers. They can be arbitrarily big or small. And naive attention mechanism use softmax to get probability distribution. And after the softmax, each number in this row, like if you sum all of them, they would sum up to 1. And then each is a probability that you can imagine that this probability is multiplied by one of these feature vectors. So in the end, as an output for this query, we got linear combination of all possible values, where each contribution is a probability in this row probability that we have from matching queries to key. And this is how it works. So there is as many keys as values. We need to remember it. There is as many outputs as queries, and each of them, key, query, value, and per query output, all have same dimensionality, which is also the number of features. Often you will also encounter multi-head attention, but it's nothing more. It's very simple. It's just, it works in a way that you take a big feature. Let's say that your keys and queries has 1024 features, and you divide them into separate bins, separate heads. So they will be processed by separate head, but each head is doing these calculations that we showed so far, just separately. So the dimensionality of our problem in the end is batch size, because it's machine learning. We always have a batch size, number of queries, number of keys, and then the last dimension is split into 2 dimensions, actually, heads number and features per head. But if you multiply features per head and heads number, you will receive back original feature size, what was on the input. Okay, and now let's jump into our topic, like the attention that we deal with. It's attention applied to graphs, and graph as a structure is always associated with a distance matrix. So here you can see this distance matrix, and this says you like what is the distance between each node, like from each of this node, what is the distance to each other node. The diagonal is 0. And this is like first thing when you try to apply attention, you will notice that wait, attention does not have any positional information at all. Actually, you need to somehow modify this mechanism to make it aware of distances. And for graphs, these distances are crucial. Like this is like, okay, each node has some feature, has some relation, some features are coded there, but this distance information is very useful. And this first idea from the paper Graph-Former works like that it adds bias terms as a function of distance to the score in attention matrix to the score before calculating softmax. So let's see on the equation, it looks very similar like a vanilla attention, just this bias term as a function of distance is added. But what kind of function, like how it is implemented? So before I go into that detail, let's also see let's check some facts. So you have as many distances as you have keys and queries, because like keys and queries code the nodes of the graph. Each pair, each node has a corresponding distance to some other node. This matrix has the same size. And the idea here is to add trainable biases, trainable parameters. We call them distance encoders, and we add them separately per each head. And it works like a dictionary. So it is a mapping from a distance index. Usually we have them like distances from 0 to 255. We support all of them in this range. And for each of the integer index, we map it to one bias, one float value. And this is these trainable parameters. So we start with random floats and we train the model, and model learns these biases per distance value per head. And in this way, it supports distances in a graphs. Nice, it works, everything is fine, but this approach has some limitations. When our client want to do a bit more advanced stuff, it's starting to be not that useful. And let's go through these limitations. So it's like relatively small number of distances. We can support it. It comes like from a fact that you can add more distances, but implementation is becoming more and more cumbersome. In CUDA, we can do 255, but if we would like to add more, it would completely change our kernel. It would be way slower, etc. So it started to be problematic for bigger distances. Also, let's look at the practical training side of things. So dataset needs to be a bit balanced to cover distances fairly. And what I mean here, like imagine that some distance is not present at dataset at all. So for this bias, this bias that match that distance will be a value that was initialized on the beginning of the training. It will not train at all. Or if you have little data, it will train something, but it will be weak. It would not be working good for these distances, whereas it can work well for other distances. And also with this limitation comes the next one. It's almost the same, like there is no generalization to unknown distances. And I'm not speaking here about like distances way larger than training dataset. No, just like if you have distance 200 and 202, but you don't have distance 201 in your training dataset, it will not generalize to this. And limited to integer distances, okay, like you could maybe have floats and have some bins, but you would have still not that big amount of these bins in practical applications. So for example, you would not be able to support distance matrix expressed as a float, for example, Euclidean distance matrix, which for graphs in chemistry is actually a good idea. Okay, so let me then introduce you to a very interesting idea, I think. It's called RoPE, from Rotary Positional Embedding. And I would try to explain you it on sequences. Take for granted that probably I would not be able to explain it good enough so you all get it. But if you find it interesting, please find some time and read about it, because I think it's super cool idea how these positional embeddings are added here. So maybe if you are familiar with training convolutional neural networks, maybe you had some experiments with adding positional info, or maybe you trained some nerves. And usually we did it by concatenating some channels, and each channel was coding some frequency. That was how it was done back then. But here the idea is different. You actually concatenate nothing. You just on the fly modify features, and you embed this positional information into the features itself. So that's why I think it's interesting, because it's very efficient in some way, and it took me some time to really get good understanding of it. But in a nutshell, it's very simple. I would start from a key property of these rotations. So we would be doing some rotations on these queries and keys, actually on their features. All these rotations I will discuss are done in pairs. And what I mean here, that they're done in pairs. So you take your entire feature vector and you divide them on pairs of indices. So like first and second feature, third and fourth feature, last and last minus one feature. And you can analyze and think in RoPE only taking one pair into account, because all other pairs works independently. So you don't have to have everything in mind that there is a many pairs and something happens between them. No, they like act independently, like in the dot product we showed earlier, like we had features that multiply and sum independently. So here we take one pair as an example, and this rotation is just visualization is just actually explanation of what happens in a complex space, but you don't have to think about complex space. You can just use real numbers and sinus cosinus function, which I will show you later how you calculate it. But for the sake of explanation, they are rotations. And like key feature, the most important feature of this entire approach, in my opinion, is the fact that if you rotate Curie by an angle n times theta, and if you rotate key by n factor n times theta, then when you calculate the dot product of them, it is the same if you would calculate dot product without any rotations of Curie and key, and then you apply rotation by an angle which is n minus n. So for now, you can think, okay, what's going on here? A lot of math, but stay with me. It's like I would explain in a second what these mn and theta are. Just here, please notice that this dot product between them would result, will end up with this n minus n effect. And that is very useful, we will find later. So back to this pair of features that we are rotating x1 and x2, they can be from keys or from Curie, it doesn't matter. And how we calculate it, we actually use this cosine sinus from m times theta, and theta is our frequency. So if you had in computer vision, you apply these channels with different frequencies for positional encoding. Here you have a theta, and each pair of features would would be good for close or far away distances depending on this theta, so different frequency in a theta. And m is actually the relative distance, because it's for sequences, for models like Llama 3, for LLMs, you would like to know positional relative position distance between tokens. So then this m is this relative position. I would show more in a detail in a second what this m actually is. You can skip w's, it's not important, they are already baked actually in the features. So this x1, x2, and cosine minus sign, this matters. And it's actually rotation matrix. If you maybe are from robotics, you probably recognize its rotation matrix. So back into the RoPE for sequences, on here we have a keys, here we have a Curies, and if we add indices, actually not add, sorry, if we minus them, like in this m minus n equation, we would get a relative distance matrix. So diagonal would be 0, and for example, this is 2 minus 0 is 2, this is 2 minus 1 is 1, 2 minus 2 is 0, etc., etc. So we have this relative matrix. Authors didn't discuss it, but I show it because for a graphs, it will matter in a second. So yeah, this is about RoPE for sequences. Sorry for being very short about this. It's really interesting if you read through a paper, I recommend it. But now let's jump into graphs. And yeah, let's start from a distance matrix for a graph. So here I have some graph and distance matrix, diagonal zeros, each node, here actually keys and Curies are, this is distance matrix, so it's like distance between each nodes. And I would ask you, like, how would you think, like, if we have distance matrix like this and not this, how could we apply RoPE for the graphs? And think about it for a second. I will give you a hint. Please recall this m minus n property as a key property. Okay, so here it is how it can be done. It's actually very simple. We can do rotations on the fly, rotating keys or Curies, however we choose. Just m minus n must agree. So we can, for example, let's say we would rotate only keys, and we would rotate them exactly as distance matrix says, but per each Curie separately. So if we are processing Curie number 1, we would rotate each keys as this row highlighted on blue. And we also could rotate Curies in opposite direction, or we could rotate keys and queries by any integer number or even non-integer, just in a way so n minus n matches what is in a distance matrix. That's actually all. So for simplicity, you will of course rotate, for example, only keys. And and here is like entire formula from original RoPE applied to a graphs. It's only the difference is that how we treat the m. So we took m not from relative position distance, but we took m directly from distance matrix, depending in which attention score cell we are processing. And here you have written down all features. For example, let's say that it's key. So all features from key. But as I showed before, it works on pairs, so you can think about it in pairs. Here it's like simplified calculations. So without matrix multiplication, here you have a dot. You have these element-wise multiplications. And this is how you calculate this RoPE. Works for graphs. Also, when you applied it. And what are nice features of this RoPE? So you have a baked positional information directly into the features. You can expect generalization to unknown distances. That means, for example, let's say that you have your training data set, and it has distances from 0 to 255, but it lacks distance 217. There is no such sample in your data set. But if you train RoPE on remaining data, it will still generalize very well, because this problem right now is just interpolation of angles you already trained, theta that you have, etc. So this would generalize very well to distances like that, which are interpolative in nature, and even I would expect slight generalization to outside of this range of training sample. Another plus is it can work with Euclidean distance matrices, so real numbers are welcome here. You can use matrix like that, and implementation is the same. The running time is the same. And faster convergence in practice, yeah, because it's easier to get grasp what the distance is. You don't have to learn each distance separately. You need to learn a RoPE formula in general, and frequency is okay. You have to learn how these frequencies works, but you see these frequencies are working for any distance that you have. Just like if you have small distances only, the long range frequencies are not rotating that much. But if you have a widespread data set, shorter, larger distances, then you can expect it generalized to everything in between. And less data to train, yeah, that's another plus. Okay, so let's sum up. Let's go back for a second and see three attention mechanisms that we discussed today. So we have vanilla attention, but it does not have any positional information at all. Both for sequences and for graphs. It will not work out of the box. But it will work for sequences, but it will not be aware of positional information. And there is a fast implementation available, flash attention from now. Maybe you have used it when you train some LLM, you probably have it already inside. Distance bias attention for graphs. It's a first approach that we and our client uses. It works. It's quite straightforward. Was not quite straightforward to get it very fast on CUDA. But it has limitations like this small range of supported distances, no generalization at all. And then we have this RoPE mechanism, which which is adapted from sequences actually to graphs. And yeah, this does not have its limitation as distance bias for attention. It has its drawbacks when it comes to implementation. It's very inefficient in PyTorch naive implementation like that. But we try to bring and make it efficient in CUDA. Okay, thank you very much.